Hey everybody, thank you for tuning in. My name is Damon Daw. I'm a PhD candidate at the City College of New York. My advisor is Carlos Murilez, and we work in the physics department. Today I'm going to talk about ponder motive trapping and guiding electrons in semiconductors. So let's get going. First, a quick outline. I'm going to talk about some of my past work and how it sort of motivated the current direction we're pursuing. I'm going to talk about the ponder motive guiding and trapping of electrons in vacuum, sort of the general theory. And then I'm going to talk about some of the unique challenges that go along with trying to apply this technique in semiconductor crystals. Briefly, the main methods I've been using for this portion of my work were theoretical. I've been using COMSOL multiphysics to do finite element analysis like electromagnetic and particle tracing. Simulations, I've also been coding in MATLAB to solve differential equations and things like that. So let's jump right in. My past work focused primarily on things like the spin and charge state of the nitrogen vacancy center. I'm not going to go into too much detail about it, but very briefly, it's a very good qubit that is a point defect in diamond, and essentially, what we started thinking about was what if we have some clusters of these defects in diamonds that are good qubits, and we can do what if we could do things like ionize the electron that's around an NV center and get it to go to another specific spot in the diamond that has like other NVs or some other defect. Could we do some interesting things with the quantum information, the spin information in those carriers if we can preserve it? So that's essentially what motivated this direction of kind of thinking about what the limits are of the control of the charge dynamics in semiconductors. And so if you're trying to move charges around inside of a crystal, the first thing you might think is why not just use a 3D electrostatic field? After all, you can use an electric field to move electrons around inside semiconductors, and it's been done for decades. So if you want to do something like confine a charged thing in 3 dimensions, there are a few conditions you need to consider for trapping. So if you want to build a trap, first of all, you're going to need a region of zero field. If you don't have a region of zero field, the thing you're trying to trap is going to sit somewhere where there's a non-zero field, and it's going to get pushed because the field is not zero, so it's going to feel a force. So you need to have a spot where the particle is going to rest somewhere, that being the net force on it is zero. So you need a region of zero field. You also need a restoring force that's pointing towards that region of zero field, something like Hooke's law force, for example, because you need the thing you're trapping to move back to the center of the trap if it tries to escape or if it gets perturbed. And you also want no other charges in the trapping region. And this is to say that you could definitely put a charge somewhere and you could trap another charge by having them stick together. But if you want to do it without having the thing just stuck to another thing, then you need no other charges in the trapping region. So you can say, well, maybe I'll set up an electric field like this. This is a static electric field, and I want no charges in here, and I want the electric field at the center to be zero. Well, you can look at Gauss's law, and you can see that this is not a divergenceless field, so there has to be some charge inside this region in order for Gauss's law to be satisfied. So we find a contradiction. And people realized this, and someone named Earnshaw first came up with this theorem. And this motivated people to think, well, this applies for electrostatic fields, but what about electrodynamic trapping? And certainly, it turned out that it was possible to use electrodynamic fields to confine charged objects. Wolfgang Paul and some of his cohort won the Nobel Prize in the late 80s, early 90s for developing this technique. And since then, it's found application in a huge variety of contexts. So one of my colleagues, Tom Delord, has done some very interesting stuff by trapping microdiamonds, so microscopic objects that are charged. And he did this in near vacuum and with some background gas. People have even used this technique to confine charged things inside of aqueous solution, so a very high drag viscous environment. And people have recently used Paul traps or ponderomotive traps to trap electrons or guide electrons at room temperature using microwave fields. So this technique has been applied across a huge range of charge to mass ratios. This microdiamond has a very low charge compared to its mass. An electron has a very, very large charge compared to its mass. And so it's a very versatile technique that can be used to do a lot of interesting things. So before we jump into some of the math, I wanted to go over just a quick simulation I did to give everyone a sort of a physical intuition for what these types of traps do. So here's a little schematic of what an electrodynamic trap might look like. This is like a 2D cross section of a three-dimensional guide. These electrodes are hyperbolic and they make a quadrupole field that oscillates in time. So these two electrodes are connected to an AC source. These two electrodes are grounded. And let's see what happens when we play this video. So you can see the red arrows are the electric field. These dots are the electrons that were released at the center of the trap. And you can see that they kind of oscillate around the center of the trap. They have a temperature, so if this trap wasn't on, they would have just flown apart and slammed into the electrodes. But since the trap is on, it's confining them to the trapping region. And you can see that they kind of undergo this very fast motion. They're kind of oscillating, but they're also sort of expanding and contracting. That very fast motion is called the micro motion, and the larger motion is called the secular motion. But we can talk more about that in a little bit. So this is just to give you an idea of the kind of physical picture you can keep in mind when we're talking about what these traps do. So now let's get into some of the nitty gritty. Here's Newton's second law for one of these traps. Notice that it has a DC part and an AC part. So usually when I'm talking about traps, I'm going to neglect this DC part. Just know that you can, besides this oscillating electrodynamic field, you can have a static field inside the trap that will let you do interesting things, although it's not necessary for trapping. You can trap stuff just with this AC part. So this is Newton's second law for the trap I just showed, for example. This is for a quadrupole potential that's sinusoidally varying. And you can reparameterize it in the form of what's a Matthews equation. It's a differential equation that looks like this. And this is an equation that's been studied for a long time. And people have realized that there's some very important parameters in this equation, especially when it comes to trapping. So one of them is this Q parameter. And some of the components of this parameter are the peak AC voltage, the mass of the thing you're trapping. This R naught is the distance from the trap center to the nearest electrode. And this Q parameter is typically known as the stability parameter. And we've got some other definitions down here for the rest of the parameterization. And what's important about this is that the behavior of this equation, or the tuning of the parameters in this equation, determine the stability and the depth of a trap. These are the two things that are very important characteristics of a trap that you need to analyze. So let's talk about what that means. So stability, if you have a stable trap, it means that the particles have trajectories that remain bounded as T becomes large. They may get smaller, meaning if this is the, say, like 1D projection of the path of one of your particles, this amplitude may get smaller because then it's still bounded. That's fine as time becomes large. the amplitude may grow, but it just can't grow to be unbounded. It can grow, but it has to grow and then stabilize or get smaller again. So you need to have trajectories that remain bounded as t becomes large. That's what stability means. Depth essentially characterizes the largest energy that a particle can have and still remain trapped. Usually this type of analysis is done using something called the pseudo-potential. This is what this psi stands for. Ponderomotive traps, like I've been saying, are electrodynamic. There's time dependence in the electric field they generate, but you can do some time averaging over the solutions to the Matthew equation, and you can get rid of the time dependence, and you can essentially say, well, we have this electrodynamic trap, but you can do this averaging and you can get an effective or a pseudo potential that represents what the macro motion of a particle in this static, non-time dependent potential would look like. And this is an example of one of the simulations that we did to characterize different electrode geometries. This is another hyperbolic guide. So when we're talking about the stability, it turns out that when you look at the Matthew equation, there are two parameters that determine the stability of the trap, the A and the Q parameters. So typically, this type of analysis is done by plotting the different combinations of A, this is A on the vertical and Q on the horizontal axis, that will lead to stable trajectories. So if you look at this diamond here, this is an overlapping region for stability in, say, the X and the Y directions. And any combination of A and Q that fall within this stability region will produce trajectories that are bounded in time. The trajectories don't all look the same. For example, if you take a spot up here in the parameter space, you'll have a 1D projection of your, say, X motion that looks like this. If you get very close to the origin, you get some nicer sinusoidal looking stuff, but still you can see the small amplitude micro motion over the top of it. And if you get very, very near the instability, so if we go from this region to anywhere outside of it, the trap will become unstable. So you get some trajectories that look like this when you get near the instability region. And finally, if you leave the region of stability, you can see that this trajectory diverges and the amplitude becomes large. So this is typically how the stability of a Paul trap is characterized. And you can generate stability diagrams like this in a few different ways, but typically we use MATLAB to solve the equation of motion numerically. And then if the solution diverges like this, we throw it out. And if the solution stays bounded, we keep it. We've also done a bunch of simulations to characterize the pseudopotential for different geometries. So this is kind of a cool one. This is a planar Paul trap. So you've got the microwave electrodes here and some ground electrodes. And you can see that the pseudopotential sort of color plot is here. And the red means it's a higher energy. The blue means it's a lower energy. So the one issue with these traps is that you can see that in the vertical here, the pseudopotential is very weak. It's pretty good on the sides, but these traps or these trap geometries generally have a lower depth on this vertical direction, so it's easy for high energy carriers to escape from traps like this. These can be convenient for different applications, but they're relatively they confine ions relatively weakly. So on the other hand, something like a linear hyperbolic electrogeometry is very good. It generates a perfect quadrupole potential, but it's pretty difficult to machine electrodes into hyperbolas, especially if you want to do something like put a crystal of silicon in here that is also hyperbolic. It's hard to machine stuff into curves like this. So a more convenient configuration we found is something that's a variant on the so-called 4-rod trap. So these blue rectangles here are the microwave and ground electrodes, and they would sit on the surface of a crystal in a configuration sort of like this. So These don't suffer from the same issues that the planar traps have, because they have a very deep pseudopotential, horizontally and vertically, and they're relatively easy to fabricate. So we just went over some of the basic theory, and some of the basic intuitions behind Paul traps and guides. And so now we're going to take the leap into the semiconductor realm and talk about what exactly are the unique challenges that we're going to face when we try to do this in a semiconductor crystal. So first, let's talk about how the equations of motion, or the Mathieu equation, might change once we go into the semiconductor. So there's a very useful theory in semiconductor physics called semi-classical transport theory. And it turns out that you can convert the Mathieu equation into the so-called semi-classical Mathieu equation that describes the dynamics of an electron wave packet inside of a semiconductor crystal. So this is the semi-classical Mathieu equation tells you how the dynamics of a localized electron wave packet will behave when you apply an external field to it, if it's in the conduction band of, say, diamond or silicon or something. And if you stay near the conduction band minimum, meaning if you don't go to very high energies, the dispersion relationship is quadratic. And this is what allows you to pack a lot of physics into this effective mass term. So this is not the bare electron mass, this is what's known as the effective mass. And it turns out that a lot of the quantum mechanics that are unique to carrier dynamics in crystals can be kind of neatly packed into this term. So we can go from the classical Mathieu equation that describes an electron in vacuum to the semi-classical Mathieu equation that describes the evolution of an electron wave packet in some semiconductor. And we don't have to pay too much for it. We just pick up this effective mass term. So that's great. We can use all the same techniques to analyze the stability and the depth of a trap that describes the evolution of an electron wave packet. But this theory only applies in the absence of collisions, or in between collisions, say. But in a crystal, there can be lots of different impurities. There can be chemical impurities. There can be missing atoms or defects. And at finite temperatures, there are always lattice vibrations or phonons. So what can we do to incorporate all these different scattering effects into our theory? So one way we started thinking about this was, okay, so the crystal is at some finite temperature, so it's hosting a bunch of phonons. There's like a phonon bath. And these phonons are the intermediary that allows the electrons or the carriers to dump energy back into the crystal. Say you photoionize a bunch of electrons in silicon by shooting them with a laser. They have a lot of excess energy. They're far above the conduction band minimum. They have to get rid of that energy somehow if they're going to go into equilibrium with the crystals. So they start emitting phonons. And so electrons can sort of dump energy into the crystal by emitting phonons. But also, once they do that, once these electrons thermalize, they emit a lot of phonons and settle near the conduction band minimum. The phonon bath is a statistical thing, so there will be fluctuations in the phonon collisions with the electrons that can inject energy back into the carriers. So we started thinking about this in terms of, say, a Brownian particle. And we think it's a pretty good way of describing the electron phonon interaction. So if you look, for example, at the electron phonon scattering rate, it goes like the density of states, which goes like the square root of the carrier energy, which is the velocity, the group velocity of the electron wave packet. So it's pretty reasonable to, like the theory of Brownian motion, say that there's some damping force or a dissipative force that's proportional to the velocity. The faster you move through the phonon bath, the more phonons you hit, and the more energy they end up taking from the electron. And then going the other way, there are fluctuations, statistical fluctuations in the phonon bath that can put energy back into the carriers. And this is exactly the type of picture that that describes Brownian motion. And there's a very convenient way to numerically quantify this damping that's described by this dissipative force term, and it's called the mobility. This mu is known as the carrier mobility, and you can rearrange some terms and find that, find that you can quantify the damping in the system using the mobility in a pretty straightforward way. One thing to mention, or an important thing to mention, is that this tau sub p is what's known as the momentum relaxation time. And it essentially just says that that collisions happen at some rate such that they erase any initial memory of what the momentum was for a carrier. So if this momentum relaxation time is very fast, then it says that an electron is going to lose any momentum information very quickly. And it essentially characterizes how quick the phonons are scattering with the electron. So if this omega is the frequency of the AC field we were talking about in the Paul trap, you want the phonon scattering rate to be much, much faster than the frequency of the AC field, because this dissipative force term, we can see we have some average brackets around here. It's an average force. So if you don't have a lot of collisions per period of your AC field, it's difficult to justify kind of packaging all those collisions into one term. So this has inherent averaging inside it, and that averaging stays valid as long as you have a lot of phonon collisions per AC field cycle. And I had mentioned some other scattering sources, like you can have impurities, you can have electron-electron or electron-hole scattering. If you get a really, really nice, very pure crystal, you can neglect impurity scattering. And if you don't generate too many carriers, like if your laser is not too intense, you can make sure that you're in a low carrier density regime. So this electron phonon term dominates over the others. So this is the most important scattering channel that we considered. So we talked about this characterization of the phonon-electron interaction in terms of Brownian motion. But let's go back and start talking about what this means for trapping. So we need to talk about what happens to the trajectory, stability, and depth of a trap when you have something like a Brownian electron that's being jostled by all these phonons. So the first modification we can make to the semi-classical Mathieu equation is to put that average drag term in. And it does something very interesting. It essentially acts as viscous damping, and it damps the trajectories of any trapped particle that's within the stability region. So if you try to trap a particle that's in some sort of viscous damping that's represented by this term mathematically, you will always get a trajectory that eventually damps down to the center of the trap. So that's good if you want to keep things tightly confined, but that's not the whole story. Because we also need to know what happens to the stability region itself when you introduce this term. And it turns out that it greatly increases the kind of space of stable parameters. So this is again A and Q, A on the vertical, Q on the horizontal. And this inset is for the b equals 0 case, and you see there's this little diamond and it ends at a little less than 1 up here. If you make b just 0.1, the edge of the diamond maybe creeps up above 1, but then if you increase b just to say something like 2.7, you can see that the shape and the region of stability kind of explodes, and you can go all the way up to, say, I don't know what this is, 17 or something, and still have stable trajectories that damp down to the center of the trap. So that's an important result, or something important to know about when you're when you're trying to build a trap that's going to trap carriers that have this viscous damping force in the equation of motion. So we just talked about what this damping term does to the stability and the stability diagrams and to the trajectories. But there was one more part, one more component for the theory of Brownian motion, and it's a random force, this fluctuating force that represents the fluctuations in the phonon bath that can inject energy back into the carrier. And it turns out that although this viscous damping term will damp the trajectories of particles down to the center of the trap, they won't just sit there, because the phonons will keep colliding with them and keep perturbing them from the center of the trap. So you need to understand essentially how big this perturbation is going to be, because if this fluctuating force is too big, it might just do something like perturb the carrier so much that it hits an electrode or it just flies out of the trap. So this term, the effect of this term is a very important thing to understand. And in general, it introduces some sigma r, or some variance in position around the zero of the trap. And it turns out that in the 90s, people developed a theory that can describe precisely what this sigma r is going to be if you know what the damping in the system is, if you know essentially what the characteristics of the collisions are. And you can get some very nice equations that will let you plug in some parameters like the mobility and the temperature, and it will tell you how small you can make the trap. And then you can use, this is the same Q parameter from before, but this will tell you the rest of the experimental parameters. So you can use this nice theory that applies in this regime. So this is one of the sort of physically justified limits we were talking about. We wanted the phonon scattering rate to be much higher than the AC frequency of the field, and indeed this theory applies just in that regime. So we think this is a good physically justified theory to use to apply to this problem. So characterizing this sigma r essentially specifies the depth of the trap. And we did some calculations, and we figured out that for silicon at a temperature of about 77 Kelvin, a few hundred megahertz, some tens of volts, you can probably get a sigma r of about 100 microns, which is pretty good. So we just talked about how treating the electron as a Brownian particle in a phonon bath modifies the equation of motion, and some of the theoretical kind of results of applying Brownian motion to a particle in a Paul trap, and how we can get a handle on the effects of the phonon scattering. So there's another really important effect that arises in semiconductor physics, and this is the effective mass anisotropy. So I talked about the effective mass a little bit ago, but it turns out that the effective mass in crystals is, in semiconductor crystals, is what's known as anisotropic. It doesn't necessarily act the same in all directions in space, and this is what I mean by that. This is a cartoon of the Brillouin zone, say of silicon or diamond, and these are conduction band energy valleys. And what that means is, for example, say you photoionize again a bunch of carriers, and you have a bunch of electrons that get a bunch of energy. They start emitting phonons, and they settle to the bottom of the conduction band. Each one of these valleys will be populated with an equal number of electrons in different energy states corresponding to the different valleys. And what's unique about this is if you apply an external field to electrons in these valleys, they will accelerate with a mass that is different depending on the angle that the external electric field makes with the crystal. So for example, if we take take an electron in this kx valley, and you apply a vertical external electric field, it'll accelerate as if it had a transverse mass that is smaller than the mass that the carrier would appear to have if you apply an electric field longitudinally along this valley. So this is a very interesting effect, and it's very characteristic of almost all semiconductors. But again, phonons can complicate this picture because phonons can exchange energy and momentum with electrons. So the electrons may equally populate these valleys at first, and if there was no scattering, they would just sit here in whatever valley they landed in. But phonons can come in and knock them to valleys on the same axis or valleys on orthogonal axes. These are called G and F scattering events. Just some nomenclature. You can also have intra-valley scattering, where a phonon comes in, scatters off the carrier, and the carrier ends up in the same valley that it started in. So if you have a very high inter-valley scattering rate, meaning the electrons are switching valleys very fast, you can essentially average over this anisotropy. So it kind of smears out the anisotropy between the transverse and the longitudinal masses, and you can use what's known as a conductivity effective mass. And that's what we were doing. That's the situation we've been considering so far with a high scattering rate regime. The high scattering rate Brownian motion regime assumes that these intervalley scattering events are very fast. But you can also think about a situation where you can have high scattering, meaning you can have, say, lots of acoustic intravalley scattering events where the electrons aren't changing valleys because of phonons. But there's still a lot of scattering. So there's still this average damping force, and there's still a fluctuating force. So they're still Brownian, but the electrons are more or less confined to whatever valley they settle in. And one way to think about this is, say we have a hyperbolic electrode guide, and we fill the space with silicon, say, and you align the crystal axes of the silicon such that they're aligned with the guide axes in a particular way, like this. Now, in this case, the two central valleys, these valleys along KZ, will have no electric field along their longitudinal axis, because the electric field, if you remember from the simulation, the electric field from the electrodes when you're trapping only acts in a 2D plane, so there's no longitudinal component. So the carriers in these two valleys will respond only with the transverse effective mass, the lighter effective mass. So we started calling these the light valleys. The other four valleys are the mixed valleys, because depending on where the carrier is in the trap, essentially depending on what the angle between the electric field and the carrier valley is, they'll respond with any intermediate effective mass anywhere between the transverse and the longitudinal effective mass. So this might happen, for example, in diamond. If you go to liquid nitrogen temperature, the intervalley scattering rate gets very low, but there's still enough acoustic phonons that are creating drag that you can still treat the particle like a Brownian particle, apply this framework we've developed, and still analyze the dynamics of the trapping or guiding. And we think you'll be able to do interesting stuff like valley polarized carriers, say, into these two central valleys, because you can tune the trap such that all the carriers in the mixed valley will essentially get to a spot in the trap where they become unstable, and then they'll be flung out of the trap, and only the carriers that were in these two central valleys will remain. So you might be able to do some interesting stuff like what I just said, polarize carriers into these specific valleys, or do something like measure the intervalley scattering rates for different semiconductors. And so one of the first things we wanted to verify was that you can trap carriers if they have a large anisotropy in their masses, and it turns out that indeed you can. Here's a simulation depicting electrons in a Paul trap, say in these horizontal valleys, with a difference in the effective masses of a factor of 20. So it's a big difference. Silicon and diamond have a factor of about 5 difference between the transverse and longitudinal effective masses. But even in a very, very anisotropic crystal, and as a factor of 20 difference, you can see that over here, the carriers are well confined in the light vertical direction. It's harder for them to be confined in the horizontal direction because they're heavier along that direction. And you can see that sort of represented in their average motion. You can see that this is the motion of the light along the light axis, excuse me, and this is the motion along the heavy axis. And so this is a nice result showing that indeed you can trap carriers that have a very large anisotropy in their effective masses. So that brings us to experiments. We went over the semi-classical equation of motion. We talked about Brownian, we talked about phonon scattering and treating the carriers as Brownian particles. We talked about mass anisotropy. And so what are we going to do to try to see this in the lab? So this is a schematic of a simple experiment that we think might work. So say this is this is a chip of silicon or diamond, and these long electrodes are the microwave electrodes. Here's a rear view of the same setup, and we have some other electrodes on either end that will apply a DC bias. And if you have the trap off or the guide off, you say like shine a laser right here, you'll get some holes to start propagating this way because you're applying a bias between these electrodes, and you'll pull the electrons this way. But they'll just be they'll be freely diffusing and moving this direction just because of the DC bias. But if you turn the trap on, it should greatly confine their lateral motion. So you'll get a lot more electrons ending up over here near the detecting pad. So this seems all pretty straightforward, but we need to make sure that we're going to be able to detect the difference between the trap on or the trap being off, and we need to be able to verify that indeed we're seeing guiding because of the microwave. And towards that end, we've done some preliminary experiments where we take a chip of very pure silicon. It's about 675 microns thick, and it's about 1 centimeter long. And we put some silver epoxy pads on the surface of this chip, and we pulsed it with a laser at different spots. And for example, if you shoot a laser at the surface of the chip, and we're using a 630 nanometer laser, by the way, you'll generate a bunch of electrons and holes, and they'll induce a current in this pad. And this is the trace you see if you're very close to the chip. If you move the laser farther away and pulse, you see sort of a similar signal, but it's reduced in magnitude. So what we need to do is have a theoretical understanding that lets us kind of parse this data or understand what we're seeing when we do these experiments. So it turns out there's a very nice theorem called the Shockley-Ramo theorem that allows you to do that. And it essentially says that charges that are near a conductor will induce an image charge. So if you start moving that charge around, you'll induce an image current in that conductor. So I did some finite element analysis simulations of this thing called the weighting field. So this equation is essentially the Shockley-Ramo theorem. It has 2 parts. You need to calculate this fictitious weighting field, and then you also need to calculate the velocity of the charge that is inducing the image current in your detector. And this is like a simulation I did representing the situation I showed earlier. So say here's one of those silver pads on the top of the chip, and here is the spot where I ionize with the laser and make a bunch of carriers emanating from this point. So I can calculate this weighting field by setting this electrode to 1 volt and setting all the other electrodes to 0 volts, and then calculating what sort of a vector field I get from that. And I can also simulate the trajectories of electrons and holes in the crystal due to photoionization. And what you see is the holes in the electrons have different signed signals, which makes sense from the Shockley-Ramo theorem. The charge of the carrier is part of the theorem, so if the carriers have opposite charges, they'll induce opposite signed signals. And one thing we had to take into account was that the mobility or the rate of diffusion of electrons and holes in semiconductors in general is not the same. In silicon, they have a difference of mobility of about 1 to 4. So in order to compensate, in order to take that into account, we set the temperature of the holes to be about 1/4 the temperature of the electrons in our simulation. And we get a pretty good qualitative agreement. Here's the experimental data, and here's the simulation. So that's a nice result, showing that we're understanding the signals we're getting out of the experiment so far, and that with a little more work, we think we'll be able to definitely show that we're achieving some sort of guiding or trapping inside of a semiconductor. So, in conclusion, we think it's going to be feasible to trap or guide electrons in, say, diamond or silicon at around 77 Kelvin. That's liquid nitrogen temperature. Some possible applications include measuring scattering rates or doing effective mass spectroscopy on the carriers. And we might be able to get even better confinement than we've calculated once we develop our theoretical and experimental understanding a little better. And I wanted to say thank you to all the people that have helped me along the way so far. This is Professor Carlos Moriles. Has been a great mentor and helped me at every step along the way. Artur Lozovoy is a postdoc who's been working with me for a long time. Has been very helpful. Tom Delord, Yunhong Wang was a very cool summer student, and our collaborators Marcus Doherty and Yunhin Cheng at the Australian National University. So thank you very much, everyone. Thanks for tuning in. I hope you liked the video. If you want to learn more about what we're doing, you can check out our website down here. And I really hope that you like the talk, and try to stay curious and keep learning. All right, thanks a lot. Bye-bye.